So we had 4 people show up for class Wednesday night. So we went ahead and lectured, went over subroutines. So I sent out a text telling y'all that the lecture was up there on a Blackboard. There's a link to Blackboard. We're supposed to watch it. What we're going to do tonight, we're going to drop back and look at what chapter is the one on not subroutines. What's the one before subroutines? Yeah, the compares. And what we didn't do, we didn't look at the master control reset. Let's go back and finish up that chapter. Well, this is jump instructions in the MCR, the master control reset instruction. Let me turn on the overhead projector. So the MCR instruction doesn't replace the e-stop circuit, right? This has to be hardware. So e-stop cannot be software. Everybody understand that? The main part of the e-stop. This can be used in conjunction with an e-stop. Now, what's the problem with using software?
The problem you reboot.
Has your cell phone ever locked up on you? You had to do a reset on it?
Hard.
Right? The hard reset on it. Computers lock up every once in a while. They get out of step. We're talking about billions of bits of information. And all it takes is the one bit to change. And bits are basically just voltage levels stored in a little type of memory called dynamic memory. And all it takes is a good electromagnetic pulse, and it could change a 1 to a 0. And if it's an instruction, it would do what? It just lock up. So this is why anything that's very, very critical we don't implement with software. So e-stops have to be implemented. The main e-stop circuit has to be implemented with hardware, but we can use the master control reset as part of that, right? Does that make sense? Used in conjunction with the e-stop circuit. Always used in pairs. So we can't use these guys. If we use one, we got to use what? Another. They're always used in pairs. The first run will be conditional, because if it wasn't conditional, it means we're going to have something. So the MCR instruction is an output instruction. So it's going to go on the right? You understand that? Toward on the L2 side. Conditional means we're going to put something between the MCR and L1. A switch or something is going to make this thing conditional. Because if it was an unconditional, then it would always skip over and not update output. The first MCR instruction is conditional, while the second MCR rung is unconditional. What does that mean? No devices between what? L1 and the MCR instruction. Disables all non-repetitive outputs between the pairs of MCR when the MCR is false. Inputs are still scanned and updated. So we don't lose inputs, but we just don't update the output. So what retentive outputs do we have? We have a retentive timer. So if it's set, if it's done or something like that, its output would remain true. And what's the other retentive devices do we have? You know, did a lab on them.
Count.
No, counters are not non-retentive.
Oh, the furniture, mattress.
No, those are not, those are not retentive. What's these right here? What's that right there? You don't see it? Latch. So that's a retentive contact. And reset. So these guys would not be disabled. So if this was latched when you came in, was inside the MCR, it would still be true, right? You understand that? Everybody okay? But it's not scanned, so it wouldn't be what? It wouldn't be updated, right? Does that make sense? So this would be one, a latch and an unlatch could be considered to be a critical output. It does not require an address, so just an MCR instruction is just an MCR instruction. Additional MCR pairs cannot be within another MCR pair. Y'all understand what that means? So you can't have an MCR between two MCRs. You can have two, you can have multiple MCR pairs, right, you understand, but they can't be within each other. Does that make sense?
You can't put a branch on it, you think?
No, I couldn't come up here. I can do this. So I could have an MCR, and then I could go down to some instruction, and then I could have another MCR. I can't put an MCR within an MCR. Now I could come over here, I could have an MCR, come down through some instructions, put another MCR, then down here put an MCR, and then have another MCR, right? Because they're not within each other. So you can't have an MCR within an MCR. Understand what I'm saying? Okay. Because it wouldn't be scanned, because it's going to skip over it anyway, right? Does that make sense? So we can have multiple MCR pairs in programs, right? It could be in a subroutine, or it could be in your main ladder program. You can have multiple MCRs, but you don't want to put a pair of MCRs within another pair of MCRs, right? Does that make sense? It does not require an address. Additional MCR pairs cannot be within another MCR pair. Used to stop operation of control systems during well, it's whatever you want to use it for. This is just what the book says. This would be, we could use this in conjunction with an e-stop, right? You understand that? User connected to the control power switch. Retentive, these are your RTOs, your retentive output timers, and your latching outputs. These are not what? Disabled. This is not in the textbook. Note that any device that must stay energized during an e-stop should be hardwired, right? Everybody understand that? Make sense? So here we got a Logic Pro, figure 11-11. So we'll run this in Logic Pro and see. I should have brought this up. We'll see if it's the right one, because it's, for some reason they don't line up. So Logic Pro, new book, figure 11.11. Oops, advanced PLCs at the top. Here we go. So here's our first MCR, right? Here's the second set MCR. So these are output instructions. The first MCR is conditional. What do we mean by conditional? Something is between what? Between the MCR and L2. Alright, so here we just have two sets or switch. So right now we go up here and we download this thing in our simulation. And we switch it to run. Okay. And here's switch, oh, wrong thing, thank you. I've been playing around with this. So here's switch 1. Okay, and output 2 is not doing anything, right? Here's switch 2, output, that's not doing anything. Here's the latch and relay, this guy's not doing anything. And here's switch 4, this is not doing anything. And why is that? Yeah, so what we need to do is we need to run this guy here. So now it's what? Active. So it's what it means it's active. Let's do it this way. So now when I do this, notice now the output, right? You understand that? It works. Now this output works. Let's latch this one. So 2 is the latch, right? No, I'm sorry. 1 is the latch, and 4 is the unlatch. Okay. So normally we would run this with a relay, with an internal relay contact. We use a normally closed. If we run it with one of our inputs, then we'll use an examiner closed, right? That makes sense. So now I'm going to come up here and deactivate it. Okay. And now output 2 0. No, that's output. So output 2 doesn't work anymore, right? Now notice what happened here. Yeah. So let's change these to switches so we can see what happens. So we got all switches, right? Okay. So now we come up here and switch 1, output 2 is turned on, right? Or 2/0. Here, this is going to turn on. Let's do all yellow so we can see them. And this guy right here is latched, right? Okay. And then of course, if I take off the latch is 3. If I hit 4, what does it do? Unlatch. And this latches. So what I'm going to do is I'm going to come up here and I'm going to turn off MCR. And notice all the unretentive outputs went what? They went off. Which one didn't come on? Which one didn't go off? The retentive, right? You understand that? So what we've done is we've turned off these outputs. Notice their lights went off over here. Their lights went off because we'll turn the MCR back on. And notice they come back on, right? See that? So what we're doing with the MCR, the Master Control Reset, is it gives us the ability to disable outputs on our PLC when the MCR is what? Active. Are we okay? Does it make sense? Any questions on this? Well, I got this off the internet somewhere. These are typical hardwired e-stop circuits. This would have an e-stop. This is a non-detent e-stop. So this is the symbol, by the way. This is the international symbol for a normally closed contact. This is normally open. So it's just basically a standard run stop circuit, right? Understand? Everybody okay? This makes sense. We can put multiple e-stops down a series string. I think I told you about the number 4 Gavilan line at USC. We must have had 25 e-stops in the series string right here. They call it a permissive circuit. And the guys would want to take a break, and guess what they would do? They hit one of these stop circuits. And this guy was 3 stories high, and every station had an e-stop circuit around there. So everything. So what we would have to do is we'd have to find out which one of these stop buttons were on. So we finally put lights on a light panel that popped up there, let them know right off the bat which one of them. Now this is the way we might wire a. So this is the screw on the 1100 PLC. This guy here has 10 inputs, and then it's got 6 outputs, right? This is, this one here, this is 1100s that we have. These guys run on 120 volts AC. Okay? All we do is just run a power cord into this, or if you're without, in the field, it would probably be hardwired to 120 volts. We make sure we run a ground, right? You understand that. Then it has a 24 volt DC power supply. And then the way this thing is set up, it's got 2 groups. So this is analog over here. So this is analog in. So this guy here's got 2 analog inputs on it. So here's the inputs that we have. So we got 10 inputs, right? Everybody okay? And notice what they've done. They've got a common for inputs 0 through 3, and then they got another DC common for inputs 1 through 9. So what we can do on this PLC is we can set these groups of inputs. We can set them up for either syncing or sourcing, depending on what we use for a common for the PLC. So if I was going to set up a syncing input, then what I would do is I either got one of 2 options. If I'm not using high-powered sensors, then what we could do is we could just come over here and take our minus, and then I would go to this common, and then I would come over here and I'd run that to this common. And then what would we do? So syncing inputs means that your input devices have to be what? If your inputs are syncing, what does your actual devices you hook up to have to be? Sourcing. So what I would do is I would come up here and I would I'll do it in red. Okay. And then I would run the red out right here. Oops, didn't switch over. Still didn't switch. I need to recalibrate my, it don't line up perfect. Okay, there we go. So I would come over here and I would run this out like this. And then all my input devices, I would just tap on to this. Now normally we do what we call a daisy chain. Y'all understand what we mean by daisy chain? What do we mean? Yeah, so what we might have a push button. And then the push button would have I'll just draw it in red, it's okay. So I'd have a push button. And then it'll have 2 terminals sticking out the back. And then I'd have another push button. You'd have 2 terminals sticking out the back. And I'd have another button. You'd have 2 terminals. What I'd do is I'd take this red and jump it to there. I would jump it to there. And I would jump it to there. So there'll be daisy chain. Does that make sense? Now up here, what we would do is we would come over here and draw it like this. And these are all push buttons. And then so I have my inputs hooked up for sourcing. I have my input devices hooked up to source, and then my PLC would be hooked up to sync. That makes sense? That makes sense? Now, if we're running high-powered sensors, which is what we usually do, then what we would do is we would have an external power supply. I wouldn't use the internal power supply, even though I could. but I'd have another external DC power supply out here somewhere. And we'll draw it like this. And then, of course, this would connect to my commons, right? You understand? And then this would go back and do what? Then we would run this to positive. We would come up here, and then this right here is where we hook our push buttons. It might be where we hook up a solid state sensor, right? You understand? It might be where we come up here and we hook up a limit switch, and then each one of them will go to a different output. But this guy's using, so my input devices himself is using the positive as the common, and then my PLC would be using the negative to common. Now, what we can also do is we could come up here, depending on where you work at and how they run things. We could set the PLC up for what? For sourcing. And how would I do that? And then what I'm going to do is I'm going to take this plus and I'm going to run it to that common, and I'm going to run it to that common right there. Or I could set one of them for sourcing and set the other one for syncing, right? You understand that? So I could come over here and set this one for sourcing, and then I could come over here and set this one up for what? Syncing, which is pretty neat. Now this PLC, the one we got, runs relay outputs. What relay outputs means, it don't care what you put out there. You can put DC, you can put AC, so you can set them up for source, you can set them up for sync, or you can set them up for AC. All you'd be concerned with is the maximum voltage that these relay contacts can handle, right? So right now I've got mine set up for sourcing output. So here's my external power supply. This is my E-stop on the previous slide. And what I do is I come up and just do what? Disconnect the power to all my outputs. Make sense? Now, if I had some critical outputs that had to stay enabled, then what we would do is we would split them up. So these two outputs would be considered critical, right? You understand? So I have them wired directly to my power source, and then these guys would be non-critical outputs. So these would be the ones that I wouldn't care if they turned on or turned off, right? That makes sense? So here what we normally do is we remove power from the output device, from the outputs themselves. So this is why just about every PLC will give you a power input to the module, so you have the ability to do what? To disconnect power to the module during E-stop. This guy's got an E-stop right here. This is the first time I ever seen an E-stop. Yeah. But so this is the E-stop right here. Can y'all see the outputs turned on? And then when oops, must be disabled. We can disable this, by the way. So I must have it disabled on this one. So if y'all pull yours out, then what should happen? Now the lights go on. But we have the ability to disable and enable this. We've been thinking about trying to actually put a real E-stop button on them things. Them things are expensive. So this is the difference between a jump and an MCR, right? So a jump must be energized to activate, right? If we have what we call a conditional jump, a MCR must be de-energized to be activated, right? You understand that? When activated, all the output instructions are run between the jump, or jumped between the jump and the label. Are they turned off? No, they're just not scanned anymore, right? You understand that? So they're not updated anymore, right? Inputs and skip runs are not updated. Outputs and the skip runs retain their state. NCA usually connected to a normally closed contact or an examine if closed instruction when using input for it. So that means if the switch opens or the circuit opens, then the MCR would automatically activate, right? That makes sense? Output instructions are not scanned. When activated, the non-retentive output instructions between the MCR are turned off. Retentive contacts retain their state, but they're not updated. Okay? That's the MCR. You got any questions on the master control reset instruction? Okay? Another thing that we didn't talk about when we went through subroutines, we did that because we had a lot of people that were absent, is that we didn't talk about interrupts. And this is in the what we talked about, we have two instructions to jump in the label, right? Okay. A subroutine, we have a jump to subroutine. And how do we specify where the subroutine's at? With a U, right? And then a file number. Okay? So here we use two subroutines. This is going to be a file number 3. This is going to be a file number 4. And we talked about how to add another program file, right? Right click on program file, and it pops up. What's the first thing we need to do? Yeah, click on new, I'm sorry. Click on new, right? And then we'll come up here, and then the next thing we need to do is enter a file number. It could be anything between 3 and 255 guys that you're managing this, right? Then we need to give it a what? We should begin the subroutine with an SBR instruction. It's a input instruction, and why they did, I don't know, but it's an input instruction. So the first instruction of the subroutine should be an SBR instruction, identified as a subroutine. And then it's got, since it's an input instruction, you gotta have an output instruction. And normally we use one of our internal relays. We don't want to sacrifice an output that's going to be on all the time, right? So this rung is scanned as true all the time. And then we come down here in the last instruction before the end, you have to put a one return. And what does that do? It takes it back to the program that called it in the rung after the JSR instruction, right? Talk about nested subroutines. What does nested subroutines mean? When a subroutine calls another subroutine, right? And of course, here we're going through 3 levels. This return is going to take it back to the rung after the JSR in the routine that called it. This return is going to take it back to this guy, right? Because this is the one that called it. This guy is going to take it back to that guy. What if we came up here and we went out to file 8 right here? Oops. So let's say later on in this program right here, I put another JSR down here, and I specified file 8. Well, what's going to happen is this is going to go out to here, right? What's it going to do when it hits the return? It's going to come back over here. It always goes back to wherever we call, whoever called it, right? You understand? It always goes back. So we can duplicate subroutines. I could use different subroutines. So So subroutine 6 could call subroutine 8. And now when it hits the what? The return is going to go back to 6 because that's the guy that called it, right? So you can go in and out of these nested subroutines. You don't have to go in order like this. Any subroutine, we can call these subroutines from anywhere, right? You understand? And when it hits that return, what will it do? It'll go back to the next rung after whatever program file called it. And what do subroutines allow us to do? Well, first of all, if I've got a sections of rungs that I notice I need to keep repeating, right? You understand? Then instead of me trying to repeat the rungs, I can do what? Yeah, and we did that in programs. You know, if we had a section of the program that needed to run every once in a while, then we would come, like, how often do I call spell check on my computer? Well, it runs all the time, right? Well, it's written as a what? It's written as a subroutine, right? You understand? So if it's written as a subroutine, who can call spell check? How many applications do we run that run? How many applications on your phone uses spell check? Yeah, just about all of them, because it's written in a subroutine, right? So any program can do what? Can call that subroutine, and then when it finishes the spell check, it's going to do what? It's going to come right back to the program that called it, right? You understand? So basically, big programs are just thousands of subroutines. That's all it is. And that's what this operating system is. It's just thousands of subroutines that I call these subroutines. An application can call the subroutine when it needs it, right? You understand? And then it always comes back to goes back to the application that calls it. So what it does, it gives us the ability to break a big program up into manageable routines. Normally what we do is we subdivide each little ladder into some type of task. And then what I can do is I can come up there, and if I have problems with something, then I don't have to find it in 700 lines of rung, right? You understand? I've written it as a what? I've written it as subroutine, and I just go into that and take care of it. Also, what we can do is we can take off this return, so I can come up here and just take this out, and then the circle will loop within that program. So I can sit there and play around with this subroutine until I get it what? Until I get it the way I want it, which is really, really neat. So we call it structured programming. When you take a big program, break it up into individual subroutines. We hate people that write what we call straight line programs. So I think I showed y'all for the pesto line. For y'all that was here. So this is one of the routines for the Festo manufacturing line that we tried to run the other night, and it didn't run because our boxes was messed up. I think we got them all fixed. No, I'm going to go here. That's not what's that. No, it's not as far as that either. So here's the program that runs one of our stations right here. This runs the processing station right here. About halfway through this program. Y'all get the idea, right? But when I come up here and look at the ladder, when I come up here and look at ladder 2, which is the main program, what's the first instruction? Substruction file 4. What's next? What's
installation stuff.
Jump to subroutine in file 6. What's the next one? Jump to subroutine in file 5, right? What's the next one? And then we actually get into a little stuff. So what we're saying, here's another one, jump subroutine file what? 3. So what they've done is they've taken this big old long program and split it up to individual subroutines, right? They got one that's called eStop, they got one that's called stop, they got one that's called blink, they got one, this one they're calling it or. Don't know how to change the name of the program file, right? How do we change the name?
Click on it.
Right click on it. Yeah, and then we can give the tab whatever. It's not going to change the file number. It's going to change the. So that's just one of the stations. This guy's got 8 stations over there, but one of them's a robot station, so it's got its own program. So there's 7 PLCs over there. Each one of them's got over 70 rungs worth of code, 80 rungs, and they've split it down into what? The subroutines, right? You understand? Which makes it more manageable, makes it easier to work with, makes it easier to edit. Makes it easier to troubleshoot. That's what I meant by edit. Another thing that we have to understand about computers is computers basically are running programs all the time. So I've got a subroutine that runs this keyboard right here. And how often does how often does my computer run that subroutine? What? Yeah, but that would be very cumbersome. So I'm not touching this keyboard, right? You understand? So it would be a waste of processor power and processor speed I'll always ask if I need something from the hard drive, to always ask the video if the video needs to be refreshed. Sitting here scanning keyboards, I only need it to run the keyboard subroutine or subroutine when I do what? When I press a key. So a long time ago, the first processor that I ever dealt with, they supported something called interrupts. An interrupt is a method where a hardware device, or we can also use, there's a software interrupt, but we don't use it that much. Basically, it's a way a hardware device can get the processor's attention without us constantly going back here and scanning. So scanning would be, and this is what I use in my class. Scanning would be I'm running my main program, and every so often, and it would be spaced out. I would say, Kareem, do you have any questions? Jover, do you have any questions? Okay. Ms. Boykin, do you have any questions? Ms. Brown, do you have any questions? Mr. Lyles, do you have any questions? Mr. Bevan, do you have any questions? Mr. Sanders, do you have any questions? What did I just do? I just wasted a ton of time for nobody needs service. Nobody needed service, but that's the way the processors originally ran, is it just come up here and everyone, it would scan all the inputs, right? You understand? So I've got all these inputs on there and it's going to scan all those inputs. It's going to run the logic and update the output. There's got to be a better way to do it. Right? What would be a better way to do it? I'm up here, you interrupt me. How would you interrupt me? Raise your hand. Okay, so now I'm up here lecturing. I'm not going to stop and scan y'all all the time. I'm not going to scan y'all, right? I'm not going to try to see if anything's out there because I know you're going to do what? You're going to interrupt me. Right? You understand that? So the computer uses interrupts. So what we do, an interrupt subroutine is almost just like a subroutine. But a subroutine requires a JSR. Right? You understand? An interrupt requires something to happen with hardware out there. So as an example, I don't know, I know where control panel is, but what we're going to do is go to programs. I don't know where it would be in Windows 10, guys, but it's out there somewhere. So we're going to go to accessories, and then we're going to go down here to this world famous system tools, and then we're going to look at system information. And then I'm going to come over here and look at hardware resources, and you see IRQs, interrupt requests. So this is everything in this system that generates and then has the ability to generate an input. Somewhere down this line is my keyboard. So now this guy here never runs the keyboard subroutine until I do what? Until I hit a key. As soon as I hit a key, the keyboard controller generates an interrupt. And then the processor says, well, who did that? And so we have a special, inside the chipset, we have something called an interrupt controller that says, well, it was interrupt number 1. Right? You understand? And so that would cause the subroutine or the routine to run that just does what? Scans my keyboard. Brings in the keyboard, then it turns its loose, right? Even though I'm up here tapping, I can type pretty fast, but I'm still in a millisecond world, and my processor's in a nanosecond world, right? So we could probably do 2,000 things before I do what? Between my keystrokes. So even that little amount of time, right? It's not scanning the keyboard. It only scans it when I do what? When I hit a key. So if that's true, then our PLCs have to have the ability to allow us to set up interrupts. And that's what this is about. So interrupts, a method available to hardware devices that can force the PLC to run a specified program file. So what we're going to do is we're going to set up another program file, but this program file is strictly going to be for what? For interrupts, right? And we got several different types of interrupts. 4 types supported by Allen Bradley: a user event interrupt. We might look at this one. I say this is we have a high-speed counter interrupt. What do we mean by high-speed counter? We have an encoder that in fact, we got them in a box back there, that gives us speed. And it gives us 2,100 pulses per revolution. So that's just one turn of the motor, right? You understand? So if that sucker was running at 600 revolutions per minute, then I would come up here and I'd multiply that by 600, and I'd multiply that by 60, and that's how many pulses I would have to count. And then so what I'm doing is I'm trying to really count things really fast. The problem they ran into in PLCs a long time ago is the counters that we've used so far are software. So every time I put a counter in my program, I insert a little subroutine in there that handles what? Counter. That handles that counter. And then later on, of course, we give it a counter number. Later on, I have another counter, and we insert another subroutine that actually handles what? That counter. Now the problem is that each one of these instructions takes time to execute. Now what was happening is that we would put these PLC counters, these software counters, on an encoder, and it lose counts because it could not do what? It could not keep up with the count. So one advantage hardware or hardwired digital circuits have over software digital logic is that hardware is always faster. So what they started doing is they started putting hardware. These guys are actually integrated circuits that's inside the PLC CPU that are hardware counters. So these guys are really, really fast, right? You understand? So what we do is that the counter, our software can't keep up with the counter, but the counter doesn't lose counts. So what we can do is we can generate an interrupt, which would go out there and it would read the counter, and then it would bring that into my program. But now we can bring the count in at my convenience, right, when we need it. Does that make sense? We have what we call a selectable time interrupt. So what this guy does is we come up here and we set up a time that we want this thing to generate an interrupt. So we could automatically generate an interrupt like every 5 seconds. By time, by whatever time we come up with. There is no STI instruction, but we have an instruction that where we can set the time this thing automatically generates an interrupt. So if we've got a really critical update that we want to be scanned every once in a while, then we can force it to scan it every 5 seconds, no matter where it's at. So we'll put this guy in an interrupt service routine by itself. It won't even be in our ladder logic. And then we can say, okay, every second you go over here and you check this input to see if it's true. Or we could actually do it in milliseconds, right? You understand that? Then we have an indent interrupt. This is what the 1100 supports. This is a hardware interrupt where we use one of our inputs. So we literally use one of our inputs. We specify it that it's going to be an interrupt input. So now something from the outside world can do what? Can generate an interrupt. And then, of course, the 504, you have to buy a module that supports interrupt. They call the screen input interrupt module. You have to buy this for the 500 series or the modular series. Everybody okay so far?
Hey, Mr. Rick,
Yeah, go ahead.
in the book it says there's a I/O interrupt, INSR.
Yeah, but he's talking generically. I'm telling you what the way the PLCs actually work. So it's an IO interrupts what they are. They call it the program that takes care of it is very similar to a subroutine, but it ends with a return. But its generated or called by an actual interrupt. Right? Does that make sense? They call it an interrupt service routine. That's what we call the program that takes care of the interrupt. I don't know if that's what it's talked about in the book or not. And this was, the book says this too, but this is not any true. An interrupt can occur anywhere in any program file. So it could occur inside a subroutine. And so interrupts have extremely high priority. So what would happen if it's inside a subroutine, then it would go out and take care of the interrupt, right, according to its priority. Different interrupts have different priorities. So the highest priority would be taken care of. Anything lower that has a lower priority, it would say, well, I'm waiting on you, and then what happened is when it got through to that interrupt, it would come back and service that. But these can occur anywhere. We don't have to put JSRs. All we have to do on select time interrupt is go up and set it out. Notice that some fixed PLC. So in the MicroLogic 1100 and also in the 500, we just have to use anything between ladder 3 and ladder 255. File 3 and 255 as our interrupt. Okay. This is where your subroutines are going to be at also, right? Now, if you're on a 1000 and you look up at your thing, then ladder 5 is going to be called interrupt. So on this fixed PLC, if you're going to use the interrupt, then the interrupt has got to be in program file number 5. For the 1100, which everybody in here should be using, all you got to do is use one between 3 and 255. Everybody okay? So that's what you got to do is find out. Interrupt instruction identifies a subroutine as an interrupt service routine instead of a regular subroutine. This is optional, but you should always use it. So that way, when you bring up the subroutine, you know what's what. It's for an interrupt, right? The first instruction must be should be a ISR instruction for interrupt service routine. This should be in run number what? 0. This is an input instruction. It's always scan true, so you got to put some type of output instruction. What we do here is use one of our bit files. Bit contact, right? Are we okay so far? 3 main types of interrupts in Allen Valley, 504, 500 series, MicroLogic controllers. We have a selectable time interrupt. Then in here we have an input port interrupt. On the 1100 it's called an input interrupt. And then on a modular PLC, you have to buy an input module that supports interrupts, right? You understand? And a user fault interrupt, by the way. So what we have the ability to do is we have to set up what we call a user fault interrupt, which means if a fault occurs inside your PLC, it will automatically, instead of freezing up and locking up everything, it automatically jump into the subroutine, which gives you the ability to maybe get in and clear the fault. I should have left the fault up there. Selectable time interrupt available on Alabama PLCs in the lab automatically generates an interrupt at a specified time interval. Are used to force scans of high priority program files at set time intervals. So we talked about that, right? We know that the longer the program is, the longer it takes to scan. In fact, I think I told y'all that originally when these PLCs or these processors were really slow, that we would literally miss input because it took so long to do what? To go through the scan, right? But what we can do here is we can set up an interrupt called a selectable time interrupt where we specify how often we want to go out there and scan this interrupt, run this interrupt service. So I have one set up for this PLC right here. Configure the STI tab. MicroLogic 500. So the 1000s, you go to the status register and you go to status 30. And then you set the time you want between the interrupts. And then status file 31, this is where you put the file number of the interrupt. It may be what? 6. R1000s is 6 for 5. So it'll be in there. If you go to 31, it'll be in there, but it'll be grayed out and it'll be the number 5. Now for the 1000s or the 1100s, which is what we have, we go to the project tree, function table, and then there should be an STI tab. And this is where we'll specify the file number and also if we want to enable or disable this interrupt. So we can disable the interrupt. This is what's nice about most of these IRQs is they can be disabled. So you can disable them for critical, if you want to ignore them, right, you understand, and then we can enable them if you need them. We'll talk about this. Are we okay? Any questions so far? No questions. This is some complicated stuff, guys.
Yeah, we'll come back to you when we talk.
That's the problem. Y'all don't ask questions in class.
So, you just configure through. So
yeah. So let's now what I have is I have the RS Logic 1000. So I'm going to bring up this guy here. And then, what we would do on the other ones is we would bring up the status file. Okay. And then we would go to these different bits. So right now, notice we don't have so up here we would have an STI where we would set, okay, this would be the time, this would be the file we're going to use, right? You understand? All we got to do is, of course, if we did this on the 1000s, and I should have that thing hooked up, we would find out it's got an STI tab up here. And ladder 5 would be great. It would be ladder 5 and it would be grayed out. Yeah, because it's stitched. For the 1100s, they give us a little more process. So it's inside the function file. And notice we have a tab up here labeled what? STI. So PFN, program file number. So this is where you would put the file number that you wanted to run when this interrupt occurred. Okay, does that make sense? And then we got 2 more bits that we would be looking at. So we would be using this one, interrupt enabled, right? 1 second. I'm sorry. Interrupt enabled, right? Everybody understand that? So we have to set this to a 1 or it wouldn't work at all. Makes sense? Time to interrupt enabled. Everybody okay? Because right now, I've got 2 things I can put in that bit. I can put a 0 or I can put a 1. Which one would you think would enable it, and which one would you think would do something? Now we're not going to have to do this, guys, because we can do this through the instruction, which I'll show you in a minute. So normally what we do is we use it through this instruction right here. So we got an instruction. Let me bring up ladder 2. And there it is, STS. This is selector time start. And then what we do here, so I'm telling this thing to automatically generate an interrupt every 5,000 milliseconds. So that would be every 5 seconds. So this is in milliseconds. You don't have a multiplier, you don't have a time base. This is in milliseconds. And if I put a 0 in here, then it's going to automatically disable it. If I put any number in there, it's going to automatically enable it for us. And then it'll come over here and it'll put the time base in there for us. So here's a set point. So right now it's set at what? 5,000. Well, I could double click on this and I could change it. But as soon as I run this program and it sees this instruction right here, what's it going to do? It's going to change it to 5,000. And I could come up here and I could disable the interrupt, but as soon as it runs it and it sees a number right here, it's going to enable it for me. So this is what we would use if we wasn't using this instruction right here. So this instruction right here is the one that's going to do 2 things for us. It's going to, well, actually 3 things. It's going to come up here and it's going to set the time for us. Now what we still have to do is what? We still have to put the file number. So if I came over here and left this 0, okay, and then I came over here and I tried to download it, right, and it's going to give me an error. It's going to give me a fault. No, it didn't. It must have kept it from last time. Let me go back and look. Oh, I didn't enter it. So this is what happened to me a while ago. I left this blank. I left it at 0. And when I ran it, the processor faulted out. Why did it fault out? Because I didn't give it a file number, right? You understand? So this is about the only thing. If we're going to use this instruction right here, this is about the only thing that we have to change. I don't know if it'll let me change it now because I'm using this instruction right there. So what we have to configure is if we're using the STS, the selectable time start, then what we still have to do is, the only thing we're going to have to do is go ahead here and specify what? File number. So right now this guy here is interrupted. How often is it interrupted? Every 5 seconds. So I'll come in here to my interrupt service routine. So we started it. There's that INT instruction. What does that identify it at? It identifies this instead of being a subroutine. We know it's a what? It's an interrupt service routine. That guy right there is optional, guys, but you need to put it up there so that way when you go back through your service, you can identify where your which ones are subroutines and which ones are interrupt service routines, right? So I've got this hooked up to switch 2. Now notice it's not updating because it's only going to do it what? Every 5 seconds. Now I just turned it off. Okay. And it's going to do it. It's only going to run this what? Every 5 seconds, right? You understand? So I'm coming over here. I've turned the switch on. You can see it become true. Because so you can actually see. So this guy here is serviced every what? Every 5 seconds. Automatically. Once I set that up. So if I've got a real high priority input that I want to constantly scan, no matter where I'm at in my program, then I can set it up as a selectable time interrupt, right? You understand? And it would automatically go, it don't lose its spot. It has nothing to do with your other program because this guy here, when it sees that return, what would it do? It'll go back to any rung it was on when the interrupt occurred. So if I've got a really, really high priority input and I want to make sure it gets scanned every 1 second, then I just go up, I can set up an STI. Now the STI itself is not an instruction, right? You understand? This is hardware. It's being done by these clocks inside the PLC. This guy right here. This is S4, by the way. We use this every once in a while to set timing. So if I wanted to flash a light at a certain speed, then I might come up here and use this bit right here. What bit would that be? S4/15. This way the light would do what? Understand that? So let's come up here in our first rung. So here's our interrupt service routine. So let's go back to main one, and then we'll just put let's put another rung here. And then I'll come up here and I'll put a contact, and then I'll put one of my outputs. There it goes. And here I'm going to put S4 colon, no, sorry, S, what was it, /15. And it automatically put a comma in there that was what? Comment. Oh yeah. And we'll assign this to another output. Output 0/ which one am I not using? Huh? We use forward. It's on the other line, and I'm not going to give it. So here we're flashing a light. We're flashing it pretty slow. This guy right here. If I wanted it to go faster, I would just drop back another bit, right? Okay. So we use this time base. It's built in there for us. We can use this time base. So back in last semester, we looked at using cross-couple timers, but it don't make sense to use a cross-couple timer when I've got what? To flash a light when I could do what? Yeah, so we could decrease the time a little bit. So let's use 12. You can look up in the book, and if you looked up at the 1100 book, it would tell you how fast these things flash, and you can add them together to get a better time. Yeah. By the way, if you was in class the other day, I was using you hear it? Yeah, that's the. So what we've done is we've created a lighting with a very simple instruction, right? Just by using that timing bit that's in there for it. Well, if I can use it, then we can set up the selectable time interrupt to also use those timing bits for us too, right? And let the microprocessor or processor do some things for us. Very simple, guys. I mean, it's very so this is being selected by the time base, and you pick out a bit, whichever bit comes closest to what you want, and you can OR them together, right? OR them or AND them together, get a more precise time if you needed a real precise time on that. So what's that in? That's in the status register. Word 4, right? Hit what? 12. And like I said, when we bring up the status register, there it is right there. So free running clock, S:4, word 4, and then you do what? You select a bit. depending on how fast you want something to flash or how fast you want to do something. But the interrupt's still occurring, right? You understand that? You can't even see it, but the interrupt is still occurring. If I come over here and turn off switch 2, then every 5 seconds it's going to do what? It's going to do this subroutine for this guy, right? Y'all understand? That makes sense? If I turn it on, oops. Then of course, depending on where it's at inside, determines when this guy out here is going to actually be activated. So that's STI, guys. And like I said, I'll try to see if we can set up something and figure out which one of these inputs up here we can use for an interrupt also. That should be in the manual for the 1100 PLC. So questions on the MCR. I think y'all have a lab that y'all are going to do on MCR. I don't think we have a lab on the selectable time interrupt. I don't think the book covers that. The book does a real crummy job. Let me go back here and go through the PowerPoints just to make sure that I've covered everything. So if you've got a 504 or if you got a 500 series, then you'll go through your status register and you'll do these bits, right? If you've got a 1000, then it's going to be in the Project 3 on the function table in the STI tab. But where would you find this information at? That's a good point. But you're out there, you got a brand new Compact Logix PLC. What you do is you just go out there and scan for the model number, and it'll bring up Allen Bradley's. So Allen Bradley gives you all these modules for free. I mean, because even if you wasn't going to buy it, they'll give you this module because it's software now anyway. It's a PDF file, and that might help them sell that PLC to you, right? You understand if they give you these manuals free. Of course, then you have the option of going out and so all ours are up on Blackboard, but I'll look this one up on my file server because it's faster than Blackboard is. So here's the instruction set. And then somewhere down this table over here is going to be what? Interrupts, using interrupts. There it is right there. And then we can close this up and zoom in on it. And it gives you a pretty good explanation. So if we're going to deal with the event interrupt, and I can just go to 172 and then just start looking and seeing how to set it up, how to enable it, how to disable it, right? Y'all understand that? But we were using the STI, selectable time interrupt. And this right here should come up here and tell you how to do what? How to set it up, right? How to enable it, how to disable it, and then of course it'll take you directly to wherever you need to go inside here. So this has links to just about everything that you can go directly to this. So if you got Allen Bradley PLCs, or even if you got Siemens PLCs, Siemens PLCs are all going to support what? Interrupts. And of course, it's probably got a timed interrupt too. It might not call it an STI instruction, but I guarantee you it's got one right out there. So that's what you would probably need to do. You know, I did get RS Logic 5000 to load in, but I hadn't got it I can't get it to connect to my PLC, my MicroLogic, my Compact Logic PLC. So this is what RS Logic 5000 looks like. Found out I had to run it as administrator. So this is the software package that Allen Bradley uses now. This is the current software package that he uses. And there's a pretty good deal of there's all type of videos on YouTube that will step you through this thing and tell you the difference between the 5,000 and the Yaris Logic 500. So this is 5,000, guys. It looks what? Looks about the same, right? So we create a new project, then we're going to have to give it a name. And then where we want to put it at. So I like this. So right now you could automatically do what? Select where you want to put these things at. And then it should open up a project tree over here on the left. And you'll probably notice something very, very fast. So here's the project tree. It's very, very similar, right? Understand that? But notice what's missing out here is your file types. You don't see a T4, you don't see a T, you don't see outputs, you don't see input. All you see is, guys, you manage the memory in this stuff. You put it in yourself. So what you can do, the way to do it is you come up here under your processor tags. And this is where you would come in and you would add, we'd go to edit tags and we would add memory. So I might want to add a T4. I might want to use T4 for timers. So by George, I could come up here and say, well, T4. And then now T4 will pop up over here, right? You understand that? So what we do on 5,000, and if you wanted to set it up like a 500, you would just come in here and do what? Just add them yourself. Yeah, but you got to add them yourself. You don't have to call them T4s. And what type of data would it be? It's going to be a what? Not an integer. We'd come down here and establish it as a what? Starts with a T. I'm just going to start typing it. Yeah. So we'd come up here and say, okay, this is a timer. So you don't have to call T4 timers. You could call it M8, but call it a timer if you wanted to. But what you could do, what most people do, is just set this up just like what? Like 500. Yeah, you go ahead but you don't have to have, if you don't use floating point numbers, you wouldn't sacrifice memory for what? Floating point numbers. Right? And if you didn't use counters, you wouldn't sacrifice memory for what? Counter. So you come in and you set up the memory the way you want to. And you don't you don't have to call it T4. It's just, the guy I looked at did it because that's the way it's called on 500. Siemens calls everything M for memory. And you set up, so we're setting up a block of memory right now for this timer. And then after that, guys, and then here's our main program. And, it's not set up yet, but it's going to look almost identical. Here's your bars, here's your users, and it's going to populate this with what we need across the top. So it's very, very similar, guys, on what we do.
So you can add something, you can make that light up. Right where the computer wrong is. Wrong, you have a contact, latch, unlatch. When you click on that right now, Mr. Rick, that's going to pop up.
Yeah, these are built in. These automatically, when you go out and so if you're using a modular PLC, you have to go out and you have to specify which one you're using. This guy, the PLC that we're using, the LE23, it automatically has a 16-bit input and a 16-bit output. But it puts it at word 1, and it puts the output at word 2. So these are built into the PLC, but what do we have the ability to do on these hybrid PLCs? We can do what? Pop the side cover off and slap another one. And then you have to come in and you have to come into your IO configuration down here somewhere and add those modules that you're adding that are not built in. So these are built into this.
It ain't like the Siemens where it picks it up and adds it itself. You gotta add it yourself on here.
Well, no, it picked it up and added it itself. If you slap a module on, the PLC, what the Siemens do is you can tell it that you can run what we call an ID and it'll go out there and do it. Now, I think the 5000 will do that for you too. It's just I don't know how to do it. So you actually go out there and once you've got communication with your PLC, you can go out there and say, hey, who are you and what do you have on you? And it'll automatically do this for you. So all it's giving us right now, but on the 1100, what we would have to do, is if it comes with a fixed number of inputs and outputs, right? You understand? But what they've taken away, guys, is they've taken away this over here because you're wasting memory. So I don't use R6. We will, but let's say I don't use R6. Well, we've already got memory dedicated to what? The R6, right? You understand? We don't use timers. Well, we've already got it dedicated to what? Timers. Now what we would do on this one, it don't do it automatically. So what we would do is that we get so many, but I would go over here to IO configuration, double click on that, and what's this over here? That's all the modules that this PLC supports that I can stick onto this right hand side. And then I would come up here and I would specify what slot I want to use for that, right? You understand? So this guy here supports 4 additional slots. 0 is built in, so that's all my built-in IO. So I can put 4 more IO modules on the right-hand side of this PLC. And then, but it's not a full-blown PLC. It's not a full-blown modular, right? So they're going to limit the number of modules we can put on the side. But I go out there and buy it. So this one don't find it either, right? You understand? All it does is know what? All it knows is what's built into it. That's all it knows. But like Gilbert was saying, what's nice about the 1200 in the TIA package is you can say unidentified PLC and it'll go out there and what? It'll go find everything on it. I mean, everything. And so it's really neat. I'll try to show y'all that too. If you deal with S7, the old version, the original version of their programming application, you have to do exactly this. It's almost identical to what we're doing here. The only thing I don't like is that the IO ports are not, the internal IO ports are not put at 0 on the 13314. They're put up at 254 and 255 by default. But you can go in and you can change those. Here we can't change the fixed IOs inside this thing. These are automatically at 0, right? Are we okay? So guys, what I'm telling you is that once you learned a little bit of stuff, even though you go to work for somebody that has the 5000, and by the way, 5000 requires, they don't call them symbols, they call them what? Tags. They require tags. And also the 1200 requires tags. So from now on, guys, when you get into these more advanced PLCs, it's not optional. 500, the tags are what? Optional. We call them symbols. These call it tags. What we usually do, and this is what I recommend on PLC 3, is set up your tag table before you even start doing what? Program. Set up your tag table because the RSLogic software gives you the tags you're going to use. Go ahead and set that thing up, and then from then on, you're just typing in words instead of trying to remember what IO is. So all these PLCs give you the ability, advanced PLCs, to set up a tag table before you set up your. So here we call them symbols. The other more advanced PLCs calls them tags. Here they're optional. In 5000 they're what? They're required. And on S7, I did programming for S7. I don't remember. So y'all got any questions?
Yeah, I did have a question. If the last wrong, we had a reset, right?
No, we just had another MCR. I don't know if we still got it up in RSLogic or not.
Right behind the unlatch. Oh, another MCR. Okay.
Another MCR. Okay. So what you have to do is you have to use them in pairs, right? You understand? Okay. You have to use them in pairs.
Matter of fact, look at it. We use that unlatch.
Yeah, so what we've done, we've got a retentive contact in here. The latch would be the retentive, right? And of course, unlatch would be. So if we have it unlatched, it's going to stay unlatched. If we have it latched, it's going to be latched, right? So the outputs are going to be on or off. These guys here are going to turn off because those are what we call non-retentive outputs, right? Everybody okay? Now, the RTO instruction, I probably need to look at that and see if the done output is set, would they consider that as a retentive contact? The only ones that they mention is the latch and the unlatch. I should have put a switch in that.
I see that other ladder logic that you had up.
What for?
Stop submitting with the,
Interrupt?
yeah, the other.
Now this is actually in the PLC. So this is actually running in the PLC.
Got that.
So here's main right here. So what does this guy right here, the STI is selectable time start, what does this do for us? Well, it allows us to enable and disable it. So if I put a 0 in my time, what does that mean? I don't know. Let's see if it lets us change it while it's running. Looks like it might. Oh no, I'm offline. Let's put 5,000 back in there. Let's go online. No, it won't let us change it. So if I come back here and take it offline and put a 0 in there, then it's going to do what to it? It's going to disable it, right? If I put any time in it at all, it's going to do what? It's going to enable it, right? So the only thing we have to do, if we use the STS instruction, the only thing we have to do is come in over here and specify in the function file and specify a what? File number. That's all you have to specify. So it says it's enabled, right? And it says timed interrupt is what? It is enabled. I've got an elevator program that I wrote for Logic Pro. You're supposed to flash the lights when the thing's in motion. And what did I use? I used the word for inside my status register. So this saves you a lot of time, guys. The one in Siemens actually gives you the time per bit. It's really cool. It tells you the time that the clock's going to flash. This right here was buried with the PLC. So that's what you'd have to do is you'd have to look this up in the manual and find out the time for each one of these bits to figure out which one. So any more questions? Okay, Tucker? And like I said, there's no lab on interrupts in the lab book, but there is a lab on the MCR, I'm pretty sure. Yeah, so this would be one of these, right? Yeah, so jump subroutine. So we have a jumper set. So we have one. I think this is just for JSR instructions. And then I think this one is for the master control relay right here. Master control reset. Would be this lab right here. So some of y'all guys some of y'all didn't finish this one. And then I had y'all do what? Skip over to here. But we really need to get some labs turned in. So right now we can go all the way down to here. So this lab group here is the jump subroutines. We have two labs that we have above it. What we're gonna do now is we'll go ahead. I think we have a test coming up next week. Y'all know Monday's a holiday, right? We didn't know Monday was a holiday? Yeah, Veterans Day. That's veterans know that. And I got my veterans. Did you see where you could get that veterans ID card? instead of carrying your DD-2 14 all around with you? Yeah. I will. So what we'll talk about Wednesday is we're going to go into logic. Logic. Everybody okay? That'd be your ands, your ors, your nots, your nands, your exclusive ors. But we're not going to do it with contacts. We're going to do it with instruction. Everybody okay? Okay, so let's go to lab.